So we're going to cover some of the basic examples of Lewis structures today in organic chemistry. But before we do that, we have to cover some of the fundamentals, and that includes the two types of bonds, how to draw them, especially when we have multiple bonds, non-bonding electrons, formal charges, and then we have our ionic structures. And so, let's get right to it. When we have ionic bonding, it happens usually when we have two atoms that have a high electronegativity difference, and they both want to complete their octet. And so what happens is, due to that high electronegativity difference, an electron transfer occurs, where essentially one of these atoms holds all the electrons really tight to itself and it holds a negative charge, and the other atom has an empty set of electrons around it and has a positive charge, and they both have their noble gas configuration at that point. But with covalent bonding, it's different. When you have two atoms that have a very similar electronegativity difference, the electrons are not pulled to one atom or the other, but rather they're shared. And so we have a share. We have like an electron pair that's shared between the two. Now, when we draw Lewis structures, we can do it one of two ways. The first way is to draw electrons as pairs, like dots. The other way to do it is to draw straight lines. And the preferred method is to draw straight lines. Now, when we have multiple bonds, we draw two lines parallel to each other. And then when you have a triple bond over here, we can draw three lines parallel to each other. And so that's what multiple bonding looks like in Lewis structures. Now, we did say that we had electrons shared as a straight line. Now, one way that it's not preferred to draw as a straight line is when we have lone pairs. Now, we know with nitrogen it has 5 valence electrons, so it has one lone pair. With oxygen it has 6 valence electrons, so it has 2 lone pairs. And then fluorine has 3 lone pairs over here. And so when we draw them in atoms, our bonds will look like straight lines, but then our lone pairs on those atoms will look like dots. And the same goes for oxygen and fluorine. Our bonds will look like straight lines, and our lone pairs will look like dots. And so now what happens when nitrogen, oxygen, or fluorine uses one of those lone pairs or has more bonds than it necessarily wants to? Then we get formal charges, which aren't real charges, but they indicate where the majority of the electron charge is, or the molecule charge is. Now, the atoms that we're concerned with are boron, carbon, nitrogen, oxygen, and then the halogens like fluorine, chlorine, and bromine. And we know what their valence electron count is, and so we have 3 different ways which we can represent them. When they're neutral, they have the desired amount of bonds, and then when positively charged, they usually have less bonds or less electrons that they want, and then when they're negatively charged, they have more electrons than they want. Now with boron, what it looks like is we have 3 bonds. This is what it normally likes to have. No lone pairs, nothing. That's exactly what it looks like because it has 3 valence electrons. When it's positively charged, it might only have 2 bonds, and so it's missing an electron that it wants and has a positive charge on it. Now, when it's negatively charged, it usually actually has 4 bonds, and so it has more electrons than it necessarily wants, and it puts on a negative charge. Now, this isn't a real charge, it's just depicting where the charge on the molecule is. Now, with carbon, it's a little different. When it's neutral, it has 4 bonds. Carbon has 4 valence electrons, 4 bonds. When it's positively charged, it only has 3 bonds, has something called a carbocation. And when it's negatively charged, no, it does not have 5 bonds actually. It has a lone pair. And so this is what a carboanion looks like. Now with nitrogen, neutral is 3 bonds and a lone pair. Positively charged is usually 4 bonds, and that gives it a positive charge right there. And when it's negatively charged, it usually has 2 lone pairs. With oxygen, we have 2 bonds, 2 lone pairs. When it's positively charged, it's sharing one of those lone pairs and now has 3 bonds and a lone pair. And then when it's negatively charged, it actually has 3 lone pairs. And so this is what negatively charged oxygen looks like. With fluorine, 3 lone pairs and 1 bond is satisfying. Positively charged would be when fluorine could have 2 bonds, and this is very rare. And then with fluorine having a negative charge is pretty normal. It's when it has its full octet, and this could be happening in an ionic bond. Now, let's give some examples. So we have over here a nitrogen with 3 hydrogens next to it, and over here I have boron with 3 hydrogens next to it. Now, we don't see any charge on this atom, but I'm going to tell you that there's going to be some formal charges in this molecule. And so over here, if we draw nitrogen as our central atom, bonded to boron, and we have our 3 hydrogens attached to nitrogen. Over here, we can right away tell that nitrogen has 4 bonds, more bonds than it necessarily wants, and so it has a positive formal charge. And boron also has 3 bonds, 3 different hydrogens, and now it has 4 bonds, which is more than the regular bonds that boron wants, which gives it a negative charge. Now these are formal charges, a positive charge in nitrogen and a negative charge in boron. But since these charges cancel out, the entire molecule actually is uncharged. Now, what about this example over here? We have carbon with 2 bonds to hydrogen and nitrogen with 2 bonds to hydrogen. We have over here carbon, hydrogen, and hydrogen. And then we have a nitrogen, and we can draw it like this with a double bond, a hydrogen, and a hydrogen. And this is to make sure that we complete the octet on all these atoms. Now, carbon over here has 4 bonds, perfectly happy. Nitrogen has 4 actually, which is not what it's used to. And so it has a positive formal charge, and therefore the entire molecule actually is positively charged due to one of those atoms having more bonds than it necessarily wants. Now, ionic structure is a little different. It's when we have like a negative charge and a positive charge coming together, but not within a covalent bond. Over here, if we draw this molecule out, we have carbon with 3 bonds to hydrogens, and then we have a nitrogen with 3 different bonds to hydrogens. Now, you see this chlorine over here? We are not going to draw it like this. This is incorrect, all right? We don't draw it this way because then we're breaking the octet rule. We can only have up to 4 bonds over here, especially with atoms only in the second row of the periodic table. What actually is happening is that since we have this positive formal charge of nitrogen, since it has 4 bonds, we actually have a negative charge on chlorine because it has 4 lone pairs over here. And it's actually drawn like this. We have our molecule with all its covalent bonds, and then we have an ionic bond over here. And so even chlorine could be like positioned somewhere as over here to depict that there's an ionic bond over here. But if you notice, positive charge and negative charge are canceling out, and so this entire molecule is actually uncharged. But in reality, what's happening is that this molecule itself, when we're concerning ourselves with this molecule, it actually has a positive charge. And so let's give some examples. Over here, we have our carbon is our central atom. It has 3 hydrogens on it, and then it has an oxygen bond to it, and that oxygen apparently has 2 hydrogens. Now, as we know, oxygen will at least have 1 lone pair, but it also has 3 bonds, which then means that oxygen has a positive formal charge on it. However, carbon is perfectly happy, 4 bonds, nothing about it is wrong. And so this entire molecule is positively charged. Now, over here on the bottom, we have a ionic structure. And how do we know that? Well, we have nitrogen over here, which is our central atom. And then we have CH3, but then in parentheses is 4, which means we have 4 of this structure. And so we can actually draw it like this, where we have 4 CH3s. Now, I can completely draw it out as this way, or I can condense it this way. Either way, it's fine. But if you are asked to draw it completely out, draw it completely out. But for the sake of space, I'm going to condense it and draw it just as this. Now, nitrogen over here has a positive formal charge. All the other carbons don't because they have 4 bonds, which is perfectly normal for them. And then we have a chlorine atom. Now, where does that chlorine atom go? Well, it's most likely over here with 4 electron pairs and has a negative charge on it. And that's the ionic structure over here. The entire structure is not charged, but however, the structure that has its covalent bonds over here is actually positively charged. And then we have another example. We have CH3 with a positive charge. Now, what would that look like? This is a carbon with 3 different hydrogens, and then it just has an empty octet. The octet on this carbon is actually not complete. And so we get a carbocation. This is actually really unstable. And so this is how you draw a carbon with a positive charge. And over here we have CH3 minus. We have a carbon with 3 hydrogens, right? But then it has a negative charge, which means it does not have 5 bonds to something, but rather it actually has a lone pair. And so we get a negative charge on here. And this is also pretty unstable. And so that concludes today's examples for Lewis structures.